Hopefully you're leading up to the next particular part. Again, when we talk about FARs, the Sn2 reactions, for the Sn2 reaction, we talked about 4 different effects. The 4 effects was the solvent, we had the substrate effect, we had the leaving group effect, we had the nucleophile effect, and finally we had the solvent effect. And for the Sn2 reaction, we talked about the substrate or the alkyl halide effect. As far as the order from fastest to slowest, (0°) followed by 1°, followed by 2°, 3°, do not occur. We also talk about as far as leaving group effect, bromine from fastest to slowest, iodine will be the fastest. Iodine comes out the fastest, followed by bromine, followed by chlorine, followed by fluorine. We also mentioned about the nucleophile effects, which there were 3 effects we talked about. We talked about as far as the strength of nucleophiles increased with a negative charge. So negative charge nucleophiles will be stronger than no charge nucleophiles. We also mentioned that the strength of nucleophiles decreased going from left to right across the period. We also mentioned that the strength of nucleophiles increased going down from top to bottom, down a column. And then we also talk about the solvent effect, and what the best solvent for Sn2 reaction would be a aprotic polar solvent, which means a solvent that cannot hydrogen bond. So what the scientists have doing, they basically took a molecule to 3° alkyl halide. You react it with water, which is in this case, a weak nucleophile. And we do it in the wrong solvent, for example, water, because water is a polar protic solvent, not a apolar protic solvent. I mean, not a aprotic polar solvent, as far as basic solvent and hydrogen bond. So when they did this reaction, they were expecting this reaction to not occur. So basically, like, oh, this reaction is not going to work. Let me go try the reaction anyway and see what happens. And guess what happened? The reaction actually occurred. And the reaction was actually faster than a typical Sn2 reaction. And what you come with the product, which replaces the halide group with the nucleophile, which is an OH water molecule. Now the scientists had a big problem. They were like, hold up. According to the Sn2 reaction, this reaction is not supposed to occur at all. And according to the Sn2 reaction, the reaction does not occur according to Sn2. Actually, this actually goes through a new reaction mechanism that was discovered in the process of actually proving that the Sn2 reaction molecule should not even occur at all. This molecule does undergo a nucleophilic substitution, but does not occur via Sn2. Now, how do you end up proving by Sn2? What you end up doing, go back to GChem, you'll take the concentration of A, because I'm going to call it A, the concentration of B, and I'm going to vary the concentration. For example, I got a concentration of A, concentration of B, and I'll end up getting a rate. if I have a concentration of A being 0.1, concentration of B being 0.1, and for example, I get like a 1 times 10 to the minus 4. Now, when I double the concentration of A, 0.2, 0.1, and my rate doubles to be 2 times 10 to the minus 4. Next, I'm going to double my concentration of B, which is my nucleophile. So 0.2 and 0.2. And my rate is 2 times 10 to the minus 4. Remember from G-Chem, what does it tell you about the rate order, the reaction order? When I double my concentration of A, what happens to the rate order of the reaction? Double. When I double my concentration of B, what happens to the rate order? What happens to the rate? What happens to the rate when I double the concentration of B? Stay the same. I would say stay the same. You're probably looking for something else, weren't you? Stay the same. By staying the same, what it tells you about the reaction, that the reaction is the rate of reaction is independent on the concentration of the nucleophile. In fact, the nature of the nucleophile does not do anything to the speed of reaction. And that's the reason why even a weak nucleophile, such as water, will react very fast in this reaction. The rate of order for the reaction only depends upon the concentration of the substrate. In this case, it's the alkyl halide. So similar to what they ended up doing for Sn1, they did the same comparison for Sn2, they did the same comparison for Sn1. We're going to look at the substrate effect, the leaving group effect, the nucleophile effect, and the solvent effect for the Sn1 reaction mechanism. Characteristics. Of the Sn1 reaction mechanism. Substrate effect. Fastest to slowest. The fastest is going to be a 3 degree, followed by a 2 degree, which is much faster than a 1 degree or a 0 degree. In fact, the 1 degree and the 0 degree are so slow that as far as the time frame of the experiment, it's considered to be do not occur. 1 degree and 0 degree do not occur. 1 degree and 0 degree alkyl halides do not undergo the Sn1 reaction mechanism. Yes?
What is that two, the little arrow? What is that mean?
This right here? Means it's so much slower.
It's much slower?
It's in fact so much slower that this reaction do not even occur. Next, we're looking for the leaving group effect. Fastest to slowest. Similar to the Sn2 reaction, the Sn1 reaction also basically depends upon how strong the carbon halide bond will be. Since carbon iodide will form the weakest bond, it will be the fast reaction, and fluoride acid forms the strongest bond, that could be the slowest reaction. The leaving group effect will be the same in both the Sn2 and the Sn1 as far as the leaving group. The fastest will still be iodine, followed by bromine, followed by chlorine, and the slowest being fluorine. Next, we'll look at nucleophile effect.
You said the slowest would be chlorine or fluorine?
Fluorine. Next, we have the nucleophile effect. Remember, for the Sn1 reaction, it is a what order reaction? First order. And it depends upon the concentration of what molecule? The substrate or the nucleophile, or both? The substrate. So what's the nucleophile effect for the reaction? No effect. The type or nature of the nucleophile for the Sn1 reaction doesn't matter. It could be a strong nucleophile, weak nucleophile. It didn't really make a difference because the strength of the nucleophile has nothing. The strength of the nucleophile itself does not come into play in the slowest or the rate determining steps of the reaction. So the nucleophile effect, even though I like listen all the single order, because I want to have a consistency between Sn2 and Sn1. But for the Sn1 reaction, nucleophile effect will be no effect. Again, I just want to list these for here so when you start doing it, you're going to have like a whole big switch between both the Sn2 and Sn1. So we're still looking at all four effects. And finally, we'll look at the solvent effect. I don't want to confuse this second part here with the Sn1 reaction mechanism I drew for the Sn2. And the best solvent for the Sn2 reaction would have been an aprotic polar solvent. The best solvent for the Sn1 is a polar protic solvent. And what is a protic solvent? A solvent that can hydrogen bond. A protic solvent is a solvent that can hydrogen bond. We also mentioned in order to hydrogen bond, a hydrogen must be directly attached to what three atoms? Fluorine, fluorine, oxygen, nitrogen. So give me an example of a polar protic solvent. Let me give an example. Drinking. Is it funny?
What you said it has to attach to what again?
So in order to hydrogen bond, hydrogen must be directly attached to fluorine, oxygen, nitrogen. So like doing phone for help. The helpline phones, FON. So fluorine, oxygen, nitrogen. Give an example of a solvent that could, of a polar protic solvent.
HBr?
Get in front of you. Water. Here's another example of a polar protic solvent. NH3. We try to get the third. Give me a third example of a polar protic solvent. Any close?
Alcohol.
I don't use HCl that much because HCl again has two little bad things with it. One is it leaches calcium out of the body, and also eats up glassware.
COH.
Yes, COH or CH3OH, alcohol. Now again, I use methanol, but the ethanol, propanol, butanol, etc. type 1. It got to be like an alcohol for the molecule that can. Alcohols are molecules that are polar protic solvents. So we got water, ammonia, alcohols. And you're probably saying, why are we even covering a particular part right here? What are we going to do? What we're going to do with a particular question? How can I ask you a question dealing with those 4 effects? I could ask you what effects involves, what are the 4 effects involved in the Sn2 reaction? Or also make you ask what are the effects involved in the Sn1 reaction? Or to make it even more fun, have you rate the order of reactions according from fastest to slowest. That's even more fun. Problem reaction. And we're like increasing or decreasing order. And increasing order. We like Sn1 or Sn2. We can do both of them anywhere. Let's do Sn1. We just kind of start with Sn1 first. And Sn1 reaction rate. Turns out would actually work out for me. Sometimes not easy easy you may think it is as far as being on the board and try to come off the top of your head as far as reacting will work. Okay, first thing we're going to do is relax. Get this one, get this one, get this one. Get all the creepers out of your head. We're going to go through our 4 effects. We're going to basically start with a little rules about as far as the effects. We're going to do substrate first. We're going to do leaving group, nucleophile, and we're going to do solve. I have a little particular process about how to do this molecule and do the reaction. The first thing we're going to do is we're going to determine what degree alpha halide we're dealing with. What degree alpha halide is molecule A?
Third.
A degree. Molecule B? 2. Molecule C? And molecule C? 3 degree. Actually, we got to go back and do one of those things before we start ranking them. We need to make sure we understand we're going for increasing order. Increasing goes from what to what? Slowest to fastest. Then we ought to make sure we go from slowest to fastest. After going through the substrate effect, can we take any molecule out? Anyone with the fastest or slowest so far after doing the degree type? Will be the slowest. The B will be the slowest. So it's 2 degree. So we know B is going to be the slowest. What do we do next? What do we look at next?
Substrate.
We did the substrate. That's the degree type. Next we're going to do is leaving group. Leaving group refers to the halides. What halides do we have? Bromine, chlorine, chlorine. According to the leaving group, which one is the fastest? Or can we distinguish out any one so far? The fastest will be?
Bromine.
Bromine. So we already know that we got A as being the fastest. We got B being the slowest. We're just trying to figure out between C and D. Next, we're going to look at the nucleophile effect. For 1 degree, what is the nucleophile effect? No effect, so basically we can ignore the nucleophile. The final thing we look for as far as between C and D, we look at the solvent effect. What is the best solvent for the Sn1 reaction? Of our solvent, we got DMSO, NH3. NH3 would be the better solvent, so that would make D the second fastest. And that would make C the second slowest. So the order would be B, C, D, A. Yes? For the Sn1 reaction, what's the best solvent for the Sn1 reaction? Polar protic or polar aprotic? Polar protic. Polar protic solvents are solvent that can hydrogen bond. If you look at a molecule, we got if you're not even sure what DMSO or NOV, but you can see that nitrogen is directly attached to hydrogen for NH3. And also, we can actually write out the structure for DMSO. We got a sulfur, oxygen, and attached to the sulfur atom will be 2 carbon atoms. Now, equal, I can ask you the same thing for Sn2. rearrange following reactions. Increasing order. Of the Sn2 reaction mechanism. Now, as far as I determine this particular one, we're going to do the same type of thing we did for the Sn1 reaction mechanism. The first thing we're going to do is identify what are we talking about as far as increasing order. Increasing order means we want to go from the slowest to the fastest. So we're going to have slowest to fastest. Now again, when we actually handle this, we're going to go through our process. We're going to look at substrate first. What degree alkyl halide is 1? 2 degree. 2. 2 degree. C. D. 2 degree. Can we rank anyone as far as fast and slowest so far? C is be the fastest. So now we've basically taken out C. Now it's down to A, B, and D. What do we look for next? Leaving group effect. What about leaving group will be our halides? Here we have a chlorine versus a chlorine versus a chlorine. Can't separate them out, point it out with. Let me try to make sure that you go ahead. Now, once you've done the leading group effect, and that's a type you give it anyone else, what do we look for next? The nucleophile effect. We have NH2, NH2, NH3. The stronger the nucleophile, the faster the reaction. Which one would be the fastest and the slowest? The fastest two would be what two? A and B would be the fastest. We don't know which one it is, but we know that D would then be the slowest. So now it gets down between A and B. The final thing to look for is going to be what? The solvent. So the solvent, we have DMSO versus H2O. What's the best solvent for Sn2? H2O. Sn2? A protein, DMSO, acetone, or HMPA are the best solvents for Sn2. So going between these two, the second fastest will be A, followed by B. And when I go through the exam, I'll make sure that we will have it so it fixes up, so we'll have like a little tie between, if I inadvertently put the little wrong salt between the wrong molecule or something like that.